Beneath the brooding skies of the Pacific Northwest, a restless giant stirs from its uneasy slumber. Once considered dormant, Mount St. Helens is sending out new warnings: deep tremors, shifting ground, strange patterns of heat and gas.
Mount St. Helens erupted, killing 57 people. Como's Theron shows us the advice from local emergency teams to make sure we are prepared for the next cascade eruption.
Ground sensors pulse with data that's hard to ignore, and satellites watch as the volcano's slopes quietly weaken. 44 years ago, this mountain unleashed the deadliest eruption in US history, erasing forests in moments and remaking the land. Now, as scientists urgently track a renewed wave of seismic activity, authorities have moved to restrict access in zones of highest concern, hoping to act before history repeats itself. How did officials know it was time to draw the boundaries tighter? And what exactly are the silent signals that have brought the world's gaze back to this infamous peak? Beneath the surface, a drama plays out in the darkness, a clash of geologic forces that shape continents, endangering lives, and redrawing the map of the Northwest. Mount St. Helens stands at the center of it all, its future uncertain, its power undiminished. So how close is this volcano to its next catastrophic awakening? And what crucial discoveries have geologists uncovered as they probe the very foundation of America's volatile Northwest? Could the next eruption come faster, fiercer, or in an entirely unexpected way? Let's descend into the turbulence simmering beneath Mount St. Helens and explore the chain of events that pushed the United States to seal off parts of the danger zone before it's too late. Chapter 1. Last warning before eruption. Every so often, a warning comes that carries extraordinary weight. For Mount St. Helens, recent alerts have grown too insistent to ignore. Scientists raised the caution level as mounting evidence put the entire region on edge. After 44 years of relative quiet, the volcano was showing unmistakable signs of stirring. But what does it mean when the experts issue such a dramatic warning? And what exactly are they detecting beneath the surface? Geologists don't sound alarms lightly. Their vigilance is methodical, based on long-term patterns. It was a combination of satellite observations and boots-on-the-ground monitoring that caught the first signs. Tremors threading through the earth, subtle but persistent. Seismicity began to spike, hinting that magma or hydrothermal fluids were on the move. Meanwhile, ground sensors picked up changes in slope, a classic indication the mountain's interior was undergoing stress. So when the signals formed a pattern, tremors, gas emissions, ground inflation, scientists knew consequences could follow. Their warning isn't about drama, it's about prevention. The decision to act, even closing down high-risk zones, hinges on recognizing these signs before disaster strikes. The community living in St. Helens' shadow must now face the question: will the next blast catch us off guard, or will we be ready? Chapter 2. Exploding earthquake signals. Suddenly, the ground shakes. An earthquake, then another and another. A rapid-fire sequence of tremors radiates from beneath Mount St. Helens, throwing scientists and nearby residents into high alert. Why do these earthquakes so often herald disaster at volcanoes like St. Helens? And what causes this seismic unrest beneath our feet? In the world of volcanoes, earthquakes rarely come without cause. In 1980, a barrage of small quakes foreshadowed unimaginable destruction. A large earthquake, then an eruption. Today, that pattern returns. Earthquakes cropping up in places once considered relatively stable, each tremor marking another warning. The underlying cause is that as molten rock or magma pushes its way upward, it fractures brittle stone, sending seismic shocks through the crust. These are magma's messages. The shaking is symptom and signal, both evidence of mounting pressure contained beneath the surface. For the trained observer, a strong earthquake swarm is less a mystery and more an imperative. a clear warning that the volcano is active and that the forces within are building. Remarkably, not all seismic activity at Mount St. Helens points to imminent eruption. Many swarms are interpreted as part of the volcano's restless nature, but when the frequency and intensity of quakes increase and line up with other risk signals, scientists know the situation is shifting. With constant monitoring, they work to distinguish natural fluctuations from those that hint at greater danger, knowing that lives may depend on correctly reading the Earth's signals. Chapter 3. Landslide Collapse Catastrophe. Picture a mountainside buckling, then suddenly giving way, a landslide roaring down in a moment of devastation. For Mount St. Helens, this isn't imagination, but vivid memory. In 1980, a magnitude 5.1 earthquake triggered a giant wedge of earth to break free, unleashing the largest landslide in recorded history and forever changing the landscape. But why do volcanoes like St. Helens experience such catastrophic slope collapses? And what makes this mountain's flanks so vulnerable today? Science tells us that volcanic slopes often grow unstable as magma rises and pressure increases. The stress fractures deep within the mountainside weaken the structure, making collapse more likely. As sensors and satellites now reveal, certain areas of the St. Helens edifice show signs of persistent movement, sometimes minuscule bulging, sometimes subsiding, always watched with keen eyes. A landslide is not merely a byproduct of eruption. It can be the trigger that exposes magma's path to the surface, opening the door to explosive force. At St. Helens, the trauma of 1980 remains central to all monitoring efforts. With each sign of new instability, fresh cracks, shifting slopes, growing evidence of subsurface stress, the need to restrict access and warn the public becomes more urgent. The lesson is clear. When the mountain groans, its sides may collapse, quickly and without mercy. Chapter 4. The Deadliest Eruption Recalled. May 18, 1980, the ground shook, the sky darkened, and Mount St. Helens erupted with unparalleled violence. This wasn't merely an eruption, but the deadliest and most destructive volcanic event in US history. Why was this disaster so severe, and how did it reshape the nation's thinking about volcano hazards? The 1980 eruption was unique. Instead of blasting vertically, pressure in the dome built until the north flank was undermined by a massive landslide. This relieved the pressure suddenly, releasing a lateral blast that swept over 230 square miles. Entire forests were leveled in moments. Pyroclastic flows, superheated clouds of gas, ash, and rock incinerated everything in their path, and the ash cloud reached across the country. Tragically, 57 lives were lost. The devastation forced a national reckoning, leading to new research, improved hazard mapping, and a more robust system of warning and emergency response. The story of 1980 guides monitoring today, and every new tremor is evaluated through the lens of these hard-learned lessons. The risk is real, the memory vivid, and the resolve to prevent another tragedy forms the bedrock of volcano science in the United States. Chapter 5. Satellite Eyes Expose Secrets. High above, satellites pass silently over the Pacific Northwest, scanning Mount St. Helens with digital precision. Invisible to the human eye, these orbiting sentinels reveal details missed by ground monitors: subtle bulges, warming soils, minuscule shifts in the volcano's profile. How do satellites unlock the secrets of St. Helens, and what have these high-tech eyes discovered that ground teams might miss? Remote sensing technology is a revolution for volcanology. Using radar, thermal scanning, and precise elevation data, scientists detect ground movements as small as a few millimeters, signals invisible to early monitoring efforts. The latest satellite data has highlighted areas of inflation and shifting slopes, critical signs that magma may be accumulating beneath the surface. These aerial observations are invaluable, confirming suspicious changes seen in instrument clusters on the ground. When ground sensors detect small uplift, satellites offer the perspective to confirm whether it's localized or region-wide. The combination of these data sources provides more reliable forecasts, and the improved detection means that authorities can refine evacuation and closure plans with greater precision and confidence. Today, The continuous surveillance of St. Helens by satellites and ground networks exemplifies the cutting edge of hazard science, an ever-vigilant warning system against the mountain's shifting moods. Chapter 6. Danger Zones Sealed Off. As the pressure mounts, literally and figuratively, the United States government and local agencies have taken the precaution of restricting access to certain areas around Mount St. Helens, including the designated high-hazard blue zone. Trails and roads in the most vulnerable areas are closed, limiting entry to essential personnel. Why do authorities take such drastic measures, and can shutting down a danger zone really prevent tragedy? The concept of hazard zones comes from past experience. In 1980, some of the worst casualties happened because people remained in the hazard zone or entered against official warnings. Some dangers can be predicted, but eruptions and collapses can unfold with little warning, making swift and decisive action crucial. Shutting down public access in volcano hazard zones is not simply bureaucratic caution, but a necessary science-based mitigation measure. By keeping people out of harm's way, casualties can be reduced if the volcano suddenly becomes more active. Monitoring, forecasting, and proactive closures form the front line of defense, turning hard-won scientific knowledge into real-world protection for local communities. As new data accumulates, authorities continually reevaluate where lines must be drawn. The guiding principle: err on the side of caution. The cost of inconvenience is far less than the price of complacency. Chapter 7. Silent Signals. Underground. Not all warnings shout, some barely murmur. At Mount St. Helens, highly sensitive instruments detect subtle but persistent phenomena from deep underground. Low-frequency earthquakes, slight increases in background heat, changes in groundwater chemistry, and quiet sighs of volcanic gas. How can such whispers spell out serious risk, and why might these faint signals offer the most important clues for predicting volcanic threats? Volcanoes often speak in nuance. Rising magma can create a series of small, deep, long-period earthquakes, sometimes too small to be felt, but clear when looked for in the data. Magma movement also releases gases, especially carbon dioxide and sulfur dioxide, which may seep out of fissures or vents in invisible plumes. Geophysicists combine seismic, thermal, and gas data into a composite picture of volcanic unrest. This web of information can hint at magma's depth, movement, and potential to erupt. For Mount St. Helens, this integrated monitoring is critical because reawakening does not always come with dramatic large quakes or visible eruptions at first. Silent signals are often the first and best warnings the Earth can give. Decoding them is key to staying one step ahead of disaster. Chapter 8. Volcanoes Out of Place. Mount St. Helens puzzles scientists not only with its activity, but also with its geography. Among the great volcanoes of the Cascade Range, St. Helens stands out because it does not align perfectly with the main volcanic trend. Why did this volcano rise in a geologically unexpected location, and what does its odd position reveal about deeper forces shaping the Pacific Northwest? Most Cascade volcanoes line up along the interface where the Juan de Fuca plate subducts beneath the North American plate, forming a volcanic arc. But St. Helens lies several miles west of this primary line, making it a subject of continual study. Research suggests that deep fractures and complex flows of mantle rock may allow magma to rise in unusual spots, forming volcanoes out of alignment. Patches of abnormally hot and buoyant mantle directly beneath St. Helens may explain its singular position. This anomaly is a reminder of the region's intricate geologic architecture, and cautions scientists that hazard models must account for more than just surface alignments. Even well-explored terrain can harbor unexpected threats, governed by the hidden forces at work far below our feet. Chapter 9. Flank Collapse. Volcanoes' Achilles heel. Some of history's worst volcanic disasters have begun not with lava or ash, but with a sudden, catastrophic flank collapse. Mount St. Helens is a global textbook case. Why are volcanic flanks such a secret vulnerability, and how does collapse lead to large-scale catastrophe? The outer slopes of a volcano are often weakened by centuries of stress, fracturing, and chemical weathering. Magma rising deep within adds further stress, sometimes prying apart the rock along ancient fault lines. When conditions are right, or wrong, A section of the edifice can give way in seconds. The consequences are twofold. The landslide itself is often deadly, and the collapse can depressurize ascending magma, triggering a powerful, explosive eruption. In 1980, the lateral blast that devastated St. Helens' surroundings followed seconds after the northern flank failed. In recent years, scientists have become ever more interested in the warning signs of flank instability: bulging slopes, increased surface cracking, and patterns of deep earthquake activity. Flank collapse remains one of the most dangerous, hardest to predict volcanic phenomena, an ever-present concern at St. Helens and similar volcanoes worldwide. Chapter 10: Seismic Swarms and Volcanic Clues. Imagine a cluster of earthquakes occurring close together in time and space. A swarm. At Mount St. Helens, these swarms are nature's coded warnings. Why are seismic swarms such reliable harbingers of volcanic unrest? And what can patterns in this underground turbulence reveal about an impending eruption? Unlike the earthquakes from shifting tectonic plates, volcanic swarms indicate magma or fluid is forcing open new fractures in the Earth's crust. At St. Helens, swarms often precede periods of heightened activity, as magma or hot groundwater moves and interacts with overlying rock. Scientists dissect these swarms, searching for information on depth, migration, and energy release, trying to determine whether the activity reflects magma ascent, internal adjustment, or a shift in the volcano's long-term behavior. At times, clusters of low-magnitude earthquakes have predated both eruptive activity and periods of dormancy, challenging geologists to refine their models. Mount St. Helens' seismic swarms remain one of the most vital and challenging tools in volcano prediction, providing precious warning despite their complexity. Chapter 11: Gas Emissions and Hidden Magma. Invisible but vital, volcanic gases seep up from Mount St. Helens, offering chemists vital clues to a volcano's state. How do scientists interpret these emissions, and what do changes in volcanic gas output tell us about magma far below? The main gases, carbon dioxide, sulfur dioxide, water vapor, each provide hints. A surge in CO2 or SO2 can indicate magma rising toward the surface, as more gas is exsolved from molten rock at shallower depths. By tracking both the amount and composition of gases escaping the volcano, geologists can often detect early signs of increased risk. Sophisticated instruments, including ground-based spectrometers and satellite sensors, measure even the faintest outgassing events. At times, gas surges have been detected before anything dramatic changes at the surface, providing invaluable early warning of unrest below. Taken together, gas data joins seismic and thermal measurements as the backbone of modern volcano surveillance, allowing scientists to see the mountain's inner workings in real time. Chapter 12: US High-Risk Volcanoes Cluster. Mount St. Helens is infamous for its hazard, but it is far from alone. The Cascade Range is a chain of active and potentially active volcanoes, several ranked as very high threat by the United States Geological Survey. Why do so many dangerous volcanoes cluster in this region, and what does this mean for communities in the Pacific Northwest? The answer lies in the dynamics of subduction. As the Juan de Fuca plate dives beneath the continent, melted rock rises to form volcanoes. The Cascadia subduction zone makes the Pacific Northwest one of the world's most volcanically active areas, with Mount Rainier, Mount Baker, Mount Adams, and Mount Hood, among several others, considered significant threats. Each volcano is unique in its eruptive style, geography, and hazards, but all draw their energy from the same powerful geologic process. For millions living nearby, the region's volatile geology demands constant vigilance and careful planning. From evacuation drills to built-in warning systems and stringent land use rules. Chapter 13: Real-time Geology, Stakes Lives. In the shadow of restless volcanoes, every second counts. For Mount St. Helens, rapid, real-time geologic monitoring is often the difference between a close call and catastrophe. Why is fast, accurate data analysis so crucial in a volcanic crisis? And how have technological advances transformed disaster response? Volcanoes move quickly. Magma injection, explosive eruptions, and landslides can unfold on timescales of minutes to hours. Real-time networks of seismometers, GPS, gas sensors, web cameras, and satellites now stream data to scientists around the clock. Teams analyze these feeds for signatures of trouble, sharp bursts of seismic energy, rapid ground deformation, abnormal gas emissions. The speed of warning means local officials can evacuate people, close roads, and mobilize emergency response before disaster strikes. Modern tools significantly improve prediction, but also bring challenges. Information overload, the need for advanced analysis, and the imperative to interpret ambiguous signals accurately. Every minute matters, and every lesson learned helps prepare for the next test, whether it's St. Helens or another Cascade volcano. Chapter 14: America's Eruption Memory. Some disasters are never forgotten. The 1980 eruption of Mount St. Helens marked a defining moment in American history. Its legacy visible both in the science of volcanology and the mindset of communities across the Pacific Northwest. Why do certain volcanic events become cultural touchstones, and how does collective memory shape today's responses? It's more than the statistics. Images of flattened forests, ash-laden towns, and the destroyed summit captured national attention. Stories like those reported by journalists such as NPR's Howard Burks resonated far beyond the blast zone. The recovery, research, and return to normal took years. The lessons shaped emergency policies and scientific priorities. Now, when new signs of unrest appear, that memory sharpens the public's focus and prompts real investment in preparedness. Survivors and residents can tell firsthand of the transformation, making the abstract threat of volcanic catastrophe visceral and immediate. The value of memory is not just to remember loss, but to inspire commitment to safety and knowledge for the future. Chapter 15: Before the Blast, Small Quakes. Volcanoes rarely erupt without warning. In almost every case, a series of small earthquakes signal the awakening. Tiny drumbeats before the main event. What makes these minor tremors so important, and why do they deserve careful attention from scientists and the public alike? In 1980, Mount St. Helens experienced hundreds of small earthquakes before any significant eruption occurred. These initial jolts were magma's first attempts to shatter old rock, to open cracks, and to find a route upward. The story repeats itself in the historical record of many other volcanoes, clusters of minor quakes preceding eruption. Today, geologists track every increase in small seismicity with the utmost care. While not every tremor signals danger, the patterns are unmistakable. Rising frequency, shallowing depths, and synchronization with gas and ground deformation warn of change. These early signs allow for life-saving actions before a full-scale eruption begins. Chapter 16: Eruption's Chain Reaction. A volcanic eruption is never just a local event. Its effects ripple far beyond the mountain's base, affecting communities, ecosystems, and economies hundreds or even thousands of miles away. How do events at St. Helens spark chain reactions? And why do distant areas feel the power of a single volcano's unrest? The scale of the 1980 eruption made this clear. Ash drifted as far as Oklahoma, affecting air quality and closing airports in multiple states. Rivers choked with ash and debris, altering fisheries and water supplies. Timber losses and property destruction cost hundreds of millions, transforming local economies. Today's interconnected world risks even greater cascading disruption. Modern air travel, power grids, and supply chains can all be affected by even modest-size eruptions. The reach of volcanic threats extends far, a constant reminder that the actions needed to limit risk can never stop at a volcano's visible rim. Chapter 17: Science versus Disaster Deniers. Every time a new alert is sounded, skepticism emerges. Some doubt the warnings, question the science, or complain about restrictions and evacuations. Why does skepticism persist, and how can scientists maintain urgency without inciting panic? Human nature resists uncertainty and inconvenience. Skeptics may underestimate the odds, forget past losses, or dismiss as overcautious the science behind shut zones like those around Mount St. Helens. But the science is real, drawn from decades of rigorous observation, refined models, and the hard lessons of disaster. The challenge for scientists and officials is to communicate with clarity, honesty, and balance. Too much alarm and trust erodes. Too little and the public may be unprepared. What's needed is simple, clear facts, timely updates, and a community-wide commitment to respecting both the volcano and the people at risk. Chapter 18. Geological Discoveries Redraw Maps. With every eruption, every landslide, science advances. Mount St. Helens has been an unparalleled opportunity to study the birth, evolution, and destruction of a volcano in real time. How do new discoveries at Mount St. Helens reshape geological understanding, and what broader insights arise from these studies? The 1980 eruption ripped open the landscape, exposing layers of Earth and giving geologists invaluable data about how volcanoes change over decades and centuries. Subsequent research has identified hidden magma reservoirs, mapped new fault systems, and refined the models that predict volcanic hazards worldwide. From ash chemistry to steam venting, every event is a clue, restructuring risk maps, refining hazard zones, and driving forward new methods for monitoring and response. With each pass of satellites, every new layer of seismic or gas data, the detailed map of St. Helens grows clearer. The knowledge gained here ripples through volcanology, informing safety planning from Japan to South America. Chapter 19. The Future of the Ring of Fire. Mount St. Helens is but one volcano of the colossal Pacific Ring of Fire, an arc of instability that circles nearly the entire Pacific Ocean. How does unrest at a single volcano relate to wider threats? And what story does the Ring of Fire tell about the Earth's inner workings? The Ring of Fire produces about 75% of the world's active volcanoes and a vast majority of its largest earthquakes. Patterns observed at St. Helens, earthquake swarms, flank collapses, explosive eruptions, mirror events at volcanoes scattered from Indonesia to Chile. Effective response to volcanic unrest, as honed at Mount St. Helens, forms a template for earthquake and volcano disciplines around the world. The interconnectedness of these hazards is a global challenge, demanding shared vigilance, rapid communication, and cross-border cooperation. For scientists and disaster specialists, every lesson learned in the Cascades may save lives half a world away. Chapter 20. Countdown to the Unimaginable. Warning lights at Mount St. Helens glow bright. Satellites detect subtle inflation, sensors record tremors, and memories of eruption urge readiness. Authorities have acted to close dangerous zones, moving decisively to avert another tragedy. Yet, in this persistent contest with nature, certainty is always elusive. Even with the best science, the timing of future eruptions is never exact. Volcanic systems can change course suddenly, and lulls may follow even the most ominous signs. The mountain teaches that force can accumulate in silence, and that every sign of quiet is only temporary. Mount St. Helens will erupt again. Of that, geologists are convinced. The only unresolved question is when the final clues will fall into place, and whether we'll be swift and wise enough to heed them. For those seeking to understand the planet's hidden forces, its mega eruptions, its mysterious interiors, its learning curve written in stone, there is no better teacher and no sterner warning than this restless giant of the Cascades. The countdown continues, reminding us to remain vigilant, informed, and always prepared.